Interference by division of amplitude by M.K. Srivastava, Department of Physics, Indian Institute of Technology, Roorkee, Uttarakhand. In this lecture, we shall take up interference by division of amplitude. Let us now go back to the setups which employ this procedure for the creation of a pair of coherent sources. That is the basic requirement anyway. Consider a ray incident on the top surface of a thin film as shown in this figure. S A is that ray. Its amplitude gets divided. It is partly reflected and partly refracted at the top surface and then reflected from the bottom surface of the film and then again refracted at the top surface. You see, AT is the top reflected beam, AB is the refracted at the point B, it is reflected BC and again comes out as CQ. So, AT and CQ are both in the reflected region. BF is the beam which is transmitted, goes through the film. Consider these two reflected beams in the reflected light. Remember, they have originated from the same beam and are therefore coherent. Their superposition gives a stationary interference pattern. The phase difference between them has been obtained earlier, you know, and is given by 2 pi by lambda times 2 mu t cos theta r. Mu is the refractive index of the material of this film, t is the thickness of the film and theta r is the angle of refraction. This thing 2 mu t cos theta r is called the optical path difference. Now, this additional factor of pi which is there is due to the difference in the nature of reflection at the top and bottom surfaces. The top reflection is at a denser medium. We are assuming that mu is greater than 1 and the reflection at the bottom surface, medium 2 air, that is at a rarer medium. So, that is why this additional factor of pi is there. The conditions for maxima and minima in the reflected light are therefore this path difference, the optical path difference as we have said is m minus half lambda, m is an in t, can be take values 1, 2, 3. This is for the maximum. Remember, this additional half lambda is coming because of that factor of pi which is there. And if 2 mu t cos theta is equal to m lambda, an integer multiple of lambda, one leads to the minimum. The two beams, reflected beams in this case are in opposite phase. In the transmitted light, the conditions are complementary to the conditions in the reflected light. So, here that additional factor of pi is not there. And that is why we have the conditions that 2 mu t cos theta is equal to m lambda for a minimum and the top condition that is for a maximum. It should naturally be like this, as there is no loss of energy. You see, there is only redistribution. Interference only causes a redistribution of energy and not a loss of energy. One thing should be noted, if the light is coming from a point source, the reflected light will be able to reach the eye only from a small portion of the film. Let us see that. This figure shows this. S is a point source. Let us consider the ray 1, top reflected, giving you the ray 3, bottom reflected, giving you the ray 4, and suppose they reach the eye. So, the eye will be able to see only this portion of the film, the portion A. Consider another ray coming from the point source, ray 2, top reflected, ray 5 goes through, bottom reflected and gives you ray 6. 5 and 6 are also coherent, they cause interference, but the light from there does not reach the eye. So, the region B will not be visible to the eye. That is an important thing here, if S is a point source. Now, so in order to be able to see the whole film, a broad source will have to be used. Let us see this figure. Now, S1, S2 is a broad source. Light coming from S1, top reflected, then again the bottom reflected, the rays 3 and 4, they reach the eye is able to see this portion of the film, the region A. 3 and 4, they are coherent, both have originated from the ray 1. Consider the ray 2 coming from another point of the source. The source is a broad source. Ray 2, top reflected, ray 4, and then no, not ray 4, it is ray 5, and the other one which is ray 6, the bottom reflected. 5 and 6 are also coherent, both have originated from the ray 2. So, the eye will be able to see the region B of the film as well. Now, remember 1 and 2 are not coherent, but they need not be coherent. The interference is between 3 and 4, they are coherent. Between 5 and 6, they are coherent. So, thus we find this is thus a big difference between the division of wavefront and division of amplitude setups. Here a broad source is a must. If you have a point source, okay, then the setup really does not work. You cannot see the whole pattern. In the case of white light, film naturally will show colors depending on the value of the thickness T of the film and the angle of refraction theta r. Now, suppose if the theta r does not vary much, suppose the light is almost parallel beam, and the film is wedge shaped, then naturally the straight line fringes parallel to the edge are formed. The fringe width in this case is given by lambda divided by 2 tan alpha. Alpha is the angle of the wedge, and if this angle is small, your tan alpha can be approximated by alpha. So, the fringe width is lambda upon 2 alpha. We are assuming that the film is a air film. Let us consider Newton's rings setup. You see, Newton's rings arrangement provides a simple laboratory setup for measuring wavelength of light. A plano-convex lens is placed on a plain glass surface. A thin film is thus formed between the curved surface of the lens, curved surface of the plano-convex lens and the plain glass plate. The thickness of the film is 0 at the point of contact, and naturally it increases as one moves away. You see, this is the setup. G is the glass plate, L is the plano-convex lens, air film is formed between the two surfaces, S is the source, L1 is this lens. So, you are a beam is coming, a broad beam. Remember, we can't have a point source here. So, a broad beam almost parallel is falling. B is a plate, glass plate, which reflects the beam down. So, the light falls vertically in normal incidence on the film. Remember, the angle theta r now will be 0, and then on top we have got a microscope which is there to observe the fringes. The microscope is focused on the film. Now, the loci of constant thickness are circles. They are circles because of the circular symmetry here, with point of contact as the center, and naturally therefore, the fringes depend on the thickness and their circular fringes are formed here when this arrangement is illuminated at normal incidence, which is the case here, which is actually always the case. The radii of dark fringes are given by mth dark fringe is square root of m lambda capital R. M can take value 0, 1, 2, 3. R is the radius of curvature of the convex surface of the plano-convex lens. The radii of the rings does vary as the square root of natural numbers. That is very interesting result. And because it is varying as the square root, this also shows that the rings will become close to each other as the radius increases. And another thing, we would like R to be pretty large if we want wide rings. If R is small, the rings will be too narrow. Now, the radii of the bright rings are given by R m is equal to square root of m plus half times lambda r. You see, this half is coming, as I pointed out before, because of that difference in the nature of reflection at the top of the film and the bottom of the film. To observe these rings, the microscope or the eye has to be focused on the upper surface of the film. You see, these films are localized fringes. Naturally, they have to be localized. They are formed where the bottom and top reflected waves, they superimpose and lead to the interference pattern. Michelson's interferometer, another very interesting device, is a precision device using division of amplitude. S is the source, P could be a screen or sometimes a lens is used to make the beam parallel, but the main thing is ultimately we have a broad source. When this light, G is a splitting plate, it splits, half of the light gets reflected, which is the ray 1, half of it gets through, which is the ray 2. Ray 1 is being reflected by the mirror M1, forms the ray 3, which falls on this plate G. Part of it is reflected, but then it goes through, becomes ray 5, goes to the observer. The ray 2, which has gone through this splitting plate, is reflected by the mirror M2, ray 4, and when this ray 4 falls back on the splitting plate G1, gets reflected, and we have the ray 6. Now, both 5 and 6 reaching the observer have originated from the same basic ray to begin with, and therefore, it forms a coherent pair and they will cause the interference pattern. You see, these mirrors are front polished mirrors. One thing you will observe here, we can think of an image of the mirror M2 formed in the splitting plate M2 prime, which is here, same distance x2 and that distance of x2 here. We can imagine that the interference pattern is a thin film type interference pattern formed between the mirror M1 and the image of the mirror M2, that is M2 prime. The distances here are x1 and x2. So, the thickness of the film, the width of the film will be really the difference between the two, that is x2 minus x1. So, that is again rays 5, 5 and 6, they interfere. This can easily be seen from the fact that if x1 and x2, as I said, are the distances of the mirrors M1 and M2 from the plate G1 and then to the eye, the waves emanating from the point P will appear to get reflected, as I said, by two parallel mirrors M1 and M2 prime, separated by a distance x1 minus x2. Here also an extended source is used. With that source, no definite interference pattern will be formed on a photographic plate placed at the position of the eye. Instead, if we have a camera focused for infinity, then on the focal plane we will obtain circular fringes, and these fringes will look like, so they have been shown here for different values of the difference of the distance, that is the thickness of the film. For a thickness of 0.3 millimeters, the fringes are very fine. As this thickness decreases, fringes become wider and wider, d is equal to 0.15 millimeters, is still slightly less, 149, and naturally when d is 0, the film will be completely dark. Remember, not completely bright because of the difference in the nature of reflection. Now, a practical point. If the beam splitter G1 is just a simple glass plate, the beam reflected from the mirror M2 will undergo an abrupt phase change of pi, as I pointed out earlier, when getting reflected by the beam splitter. And since the extra path that one of the beams will traverse will be twice of x1 minus x2, the conditions for destructive and constructive interference will be twice the difference x1 minus x2 cos theta equal to n lambda for destructive interference because of additional factor of pi, as I pointed out earlier, or m into lambda plus half for constructive interference. As d decreases, that is why the distances x1 and x2 approach each other, the fringe pattern tends to collapse towards the center. And naturally, conversely, if d is increased, the fringe pattern will expand. As d is being increased, the fringes will appear to originate from the center. That is the idea. Now, if n fringes collapse to the center as the mirror M1 moves by a distance d naught, then we must have this relation 2d is equal to n lambda as before. Now, the distance has changed by d naught, so 2d minus d naught, n fringes have disappeared, have collapsed. So, m minus capital N times lambda. Here theta has been put equal to 0 because we are looking at the central fringe where the light is incident normally. So, cos theta is 1, and thus from these relations we find that lambda is equal to 2 d naught divided by n, and this provides us a method for the measurement of the fringes. Look at the circular fringes, move the mirror, count the number of fringes which have collapsed, and you get a capital N. You have measured D naught, you can find out the wavelength. Now, another problem, simple problem though in this setup. In an actual interferometer, the beam splitter G1 is not a line, it consists of a plate naturally, which may be about half a centimeter thick. The back surface of which is partially silvered, such that 50% light goes through, 50% is reflected, and these reflections occur at the back surface. This is the picture in an actual Michelson's interferometer. The beam splitter G1 is a plate of about half a centimeter thick. Now, you see the light which is coming is partially reflected at the back surface, half of it going towards the mirror M2 straight and half of it going to the other mirror, and then reflected from there. The main thing to be seen is the distance travelled in the plate G1 is not same for both the beams. We find that the beam 5 traverses the glass plate 3 times, and in order to compensate for this additional path, one introduces a compensating plate G2, which is exactly of the same thickness. The compensating plate is not really necessary for a monochromatic source, because the additional path twice n minus 1 into T, n is the refractive index of the material of this compensating plate. This is the additional path introduced by G1. It can be easily compensated by simply moving the mirror, no problem, by this much of distance, n1 minus n minus 1 into T, where the difficulty is for a white light source, it is not possible to simultaneously satisfy the zero path difference condition for all wavelengths, since the refractive index depends on wavelength. Note this point. We want to compensate for this additional path difference of the light through the splitting plate, and this should be there satisfied for all the wavelength components present in the white light. But this by itself is not possible, because the optical path difference, depending on the refractive index, depends on the wavelength. It cannot be compensated for all the wavelengths at the same time. Let us see that. For a wavelength of 6560 angstroms and another at 4861 angstroms, the refractive index of crown glass, for example, is 1.5244 and 1.5330 respectively. Now, if we are using a 0.5 centimeter thick crown glass plate as the beam splitter G1, then the mirror M1 should be moved by 0.2622 centimeters for the wavelength 6560 angstroms, and it should be moved by 0.665 centimeters for wavelength 4861 angstroms. They are not same. Not only that, the difference between the two positions corresponds to over 100 wavelengths. Thus, if we have a continuous range of wavelengths from 4861 angstroms So, 6560 angstroms as we would have in a white light source. The path difference between any pair of interfering rays will vary so rapidly with wavelength that we would observe only a uniform white light illumination, no pattern. In the presence of a compensating plate G2, see, now all this problem gets eliminated right away. Whatever happens in G1, it gets compensated by G2 for every wavelength component present in the white light. One would be able to observe a few colored fringes around the point corresponding to 0 part difference. Okay, and the interesting measurement can be carried out. This is the measurement of difference between the two close wavelengths. Can also be used to measure difference in wavelengths if the light used has two close wavelengths, lambda 1 and lambda 2, with the difference being very, very small compared to the individual wavelengths. If the difference d in the distances of the two Michelson's mirror is such that 2d is equal to an integer times lambda 1, but is equal to m plus half times lambda 2. See, I have assumed lambda 2 being smaller than lambda 1. So, for lambda 1 is an integer multiple, for lambda 2 is an integer plus half multiple. Then what will happen? The bright fringes of lambda 2 will fall on dark fringes of lambda 1 and the total fringe pattern will disappear. The wavelength difference can be calculated and is given by lambda 1 minus lambda 2 is equal to lambda 1 lambda 2 divided by 4 times d. Lambda 1 lambda 2 can be written as lambda square, which is the mean wavelength. So, the result is lambda 1 minus lambda 2 is equal to lambda square upon 4d. Newton's rings arrangement can also be very easily used to study and demonstrate this and measure the difference lambda 1 minus lambda 2. You see, we know the path difference here is related to the radii of the rings. 2d is equal to small r square upon capital R. Small r is the radius of the ring, capital R is the radius of curvature of the plano-convex lens used in the arrangement. So, the above relation therefore becomes lambda 1 minus lambda 2 is equal to lambda square times capital R divided by 2 r square, or in terms of r square is equal to lambda square capital R divided by twice lambda 1 minus lambda 2. So, this relation gives the radius of the ring where the fringe pattern vanishes. And the method could be to lift the plano-convex lens. Remember, you have a plano-convex lens placed on a glass plate. Now, we are lifting it. So, the path difference at the point of contact, you see, at the point of contact the thickness is 0. Now, we are increasing that thickness. The path difference at the point of contact becomes such that this point now corresponds to maximum for one wavelength and minimum for the other. So, if d is the distance through which the lens has been lifted, then this d will be equal to lambda square divided by 4 times lambda 1 minus lambda 2. With Michelson's interferometer, one can have a different method. One can keep moving one of the mirrors to obtain the distance required to be moved for 2 consecutive vanishing of the fringes. Let us understand this. Suppose for a certain distance the fringe pattern has vanished. This means maximum of one wavelength falls over the minimum of the other. You keep moving the fringe, one of the mirrors. A situation will come when the fringes will appear again. Continue to move the fringe, the mirror. Again a situation will come when maximum of one wavelength falls over the minimum of the other and the fringe pattern vanishes. This is what we are talking here. One can keep moving one of the mirrors to obtain the distance required to be moved for 2 consecutive vanishings of the fringes. If this distance is d prime, then this d prime is equal to, as before, lambda square divided by twice lambda 1 minus lambda 2. So, this method can be used to find the difference between 2 closed wavelengths present in the light coming from the source. Okay, I think with this we have come to the end of this lecture. Thank you.